So, good afternoon, guys. We are starting today on the Linux kernel certification course from IR Labs on virtual memory overview. So, virtual memory basically this particular session is the agenda is to understand the concept of virtual memory and the addressing in the inside kernel, how the processes are laid down, how the mapping is being done from the process address space to the physical memory mapping, and what is the concept behind the virtual memory and how it is implemented. So basically code browsing would not be possible in this class, but we'll go through the concept first, and then we'll try to map some major data structures into it. So Jitu, are you able to hear me? All right. So is my voice clear? Okay. So the today's agenda would be the types of memory. Paging is the concept. Basically, you divide memory or addresses into small chunk and the pieces, and we call it pages. So we do the minimum unit of dealing with address chunk is the paging, and this is how the kernel implemented the virtual memory concept using page mappings from the address space, process address space, to the physical address space. So paging will read about how the mapping is being done through the page tables, how that what is TLB, translation look aside buffer, why it is needed, and where it is actually giving you a performance edge. um, Fragmentation is another concept. While designing any operating system and the memory layout, basically you may end up um, uh, end up with the vacant space. So internal, there are two kind of fragmentation which the problem arises in any of the models. So internal fragmentation and external fragmentation, and I mean, there is a pros and cons. Basically, fragmentation is just is a problem arises in the different architectures. So that depends what kind of architecture we are using in kernel, will lead to the fragmentation problem, either internally, or it's an internal fragmentation problem or external fragmentation problem. Demand paging is another concept which basically deal with making the pages available which is required for the execution of the processes, and page replacement algorithms is there. Okay, so you are running with the limited physical memory always, all the time, and you might be having a larger active virtual memory. So in that case, if you have active virtual memory, um, active virtual memory is larger than your physical memory size, it usually swaps out the pages, and swap out is the basically that concept. You whenever you install Linux operating system, you reserve some of the swap area, which act as a extendable physical RAM, basically extendable RAM, which is created on your hard drive. So swap out, swap in is a IO to the to the hard drive basically. So whenever our active virtual pages goes larger in number than your physical memory, some pages um, need to be swapped out from the memory, so that memory is available for the critical applications and the critical response. And we will go through each and every topic for today, so that we could be able to understand how memory is actually laid out in this. So okay, this is an important one. Basically when we um, talk about memory, when we say the resources and the computing resources, so we mean to say the CPU, basically your computing unit is the CPU. Then memory is basically RAM. When we say it, we refer it as a main memory or real memory. Then we have hard drives, which is secondary memory, or it is a permanent memory on the disk. And basically we need RAM for the faster access of the chunk of memory. So how it is being managed between how your CPU accesses that memory. And the first thing is RAM is just a memory, but due to its random accessibility to the any of the location, it is called as RAM. So we use RAM for the performance purpose. We don't need to go to sequentially, like we need to go through accessing our hard drive. So it's a sequential access, because once your head is at the 0th sector, it will have to move to 1000 sector. It has to read the page number. Page resides at memory location 1001. So it has to travel all those sectors, 1000 sectors, and it's a sequential. But the random access is your RAM is providing you the access, or reading any chunk of data, or accessing anything. The head doesn't go. It is a responsive to through the data bus. So, and virtual memory, and obviously virtual memory basically resides conceptually. And I would say, if you have let's say you have 2 GB of memory, RAM basically, which is used by your processor to basically enable the processes to execute. We cannot run more than multiple processes into it, because we always have a limited memory to our system. But how you can enable multiple processes, scaling it out and using more computing power of your system. So this is where the virtual memory comes into the picture. And virtual memory is a concept that processes always think that this much memory I have. So they see always virtual memory as the memory available to the system. But this is your virtual memory manager, which manages that memory and make it available to the physical memory. So two step of mapping is, your process has the set of addresses. Let's say you have 32-bit process, so you will have address space of 4 GB, and each and every byte in your process address space is mapped to your virtual memory. And virtual memory is a conceptually a mapping. So let's say I have 32-bit process and 49-bit of virtual memory. I could map lot of processes in my virtual memory, right? Because 2 to the power 32, if you divide it, how many if I have 49-bit of virtual memory, you can divide it how many actual processes that can be supported by the system. But I mean, there are multiple other problems like thrashing and all that. We'll go into that later on. Will probably, it is a more subjective than this, how many processes will be supported. But this is how you can scale your system to use more computing, right? So we will see, the first thing is paging. Basically what is the paging means you divide your whole address space into smaller chunk of memory addresses. So let's say I decide a page size of 4K. Okay. So you can divide it with 2 to the power 32 and 4K. These many pages will be there. So if you have 4K, if you have 4K of page size, and if you have 32-bit of process, then you will be addressing 2048 pages. Not 2048, it would be nearly 1024 multiplied by 1024, right? These many pages will be there in your process address space. Now these many pages, so active pages which are required to be mapped to virtual memory is going to get the memory addresses, in virtual memory. So you have I'll tell you how it gets global descriptor for any processes, because basically kernel maintains an algorithm to identify what is the starting point of any of the process. So page table basically resides per process. You need to have mapping of each and every page of the processes, and where it is actually mapped to the virtual memory, your virtual memory, the whole virtual memory. So we'll see it here in the picture. So whatever, let's say I have I told you that if you have taken a page size, let's say 4K, then that offset bits will be 12 bits. Just assuming that this is a logical address, not the virtual address. Don't assume it as a virtual address right now. Assume it as a logical address here. So your logical address will be having 12 bits of offset if you have 4K of page size, and rest of the 20 bits will be the page table reference and number and page table descriptor. Okay. Now once you get the global descriptor table will give you the map of the process initial virtual address space. So that translates some of the larger bit numbers, and that helps you to create a virtual address. So any of the processes, any page on the process address space will be having a definite mapping to the virtual address space. So page table entry, okay, this will go through the page tables. Alright, so This is nothing much. It is um, basically your more of the metadata to the process. um, so your process is basically assuming that it needs 4 GB. Let's say your 32-bit process, it just needs 4 GB of the memory to execute it itself. But basically we in the systems, we it is very difficult to find 4 GB of RAM everywhere to run single process. So what you do, you tell process that okay, you have a larger memory available, you can map your pages to this larger memory. Now this virtual address space, which is mapping lot of processes pages, is a subsystem virtual memory manager is going to manage those pages into the main memory, which is quite smaller in size. So the approach is to then you need to keep lot of bookkeeping and metadata per process, uh, as a global data to the whole system. So virtual memory will have a global descriptor table which will keep mapping of the process per process basis, the index numbers. So once that index number is generated by the virtual memory, you will have the index to the uh, to the global virtual memory addressing. And once you have that indexing, from there you will have the process address mapping to the virtual addresses. So every every process, as I told you, that if you have 4K of the pages, you will have 1024 multiplied by 1024 pages, and these pages will map to a virtual address on the whole virtual memory addressing. So this is maintained by your page table. Now this page table is maintained per process, and we will see on the next diagram how it is done. So as I told you that um, that per process is like your addressing scheme is what is how much bit process is running is going to decide the address space of the process. And the process that process index will be defined by global descriptor table, which will give you the index at the virtual address. Now virtual address to physical, where exactly that page is sitting on the physical memory, is this is the mechanism. So you have one virtual address, that virtual address you actually uh, get the page table reference from the 20 bits of if it is 49 bit virtual address space, it would be like and 4K of the paging scheme. As you can remove offset of the 4K, that is 12 bytes, and you will have 37 bytes, which is going to define the page table. And um, so I'll tell you how to map it. Basically, you have a page table PTR register. So some of the bits on the page number will reach to the um, um, will be processed with the page table PTR register, and it will give you the reference of the frame number in the page table entry. Okay, so how you will reach there is uh, okay, I need to draw one more picture so that you could be able to understand it more properly. um, it is not that complex, but basically so much of conceptual implementation. So how you will reach to a page in the main memory is shown here in this address translation. So uh, okay, so this register is basically again uh, It is basically, um, you do a XOR with the page table PTR with the 8 bits, with the first 8 bits of the page number. So once you do a XOR with that, you will actually get a address, right? And that address that address is actually the index, and that number is actually an index on the page table. Okay, and that page table, uh, index at the page table, so you basically see it like this. So whatever the 8 bits, first 8 bits of the page number is processed with the page table PTR, and you get a addition which is actually index addition. How you will find, um, how you will find where this page table, because a lot of page tables will be residing in the system, and this page table PTR will give you the index of this page table, and this page number will help you to reach to the frame number of this page table. And once you reach to that frame number, you process it with the uh, uh, with the offset which is coming last 12 bytes of the virtual address space. You will reach to the actual byte on the physical memory, and whatever the whatever the value you will get it here is actually address in the physical memory. So so the core of it is offset. We are not touching anymore. We are keeping that offset 12 bytes always same all the time. Okay, and the main magic happens in between the page referencing and the page table PTR, which is per process, and it gives you the index on the whole page table entries. Okay, so whole page tables. So once you reach to the your particular page table, this PTR helps you to reach to your particular page table, and uh, this page number helps you to reach to the frame number. So once you sum it up, you will reach to the frame number, that index of the frame number in the whole page table entry, and here you will find the frame number written. So frame number, you will frame number means this is the frame number on the physical memory. So this is mapping, right? You will have index numbers here, right? And you have a frame number which basically keeps mapping the physical memory frame numbers. Okay, so once you have that frame number, you will reach here, because this page number 8 bits and this page table PTR actually processes, it gives you the index. The page table PTR will reach you here, this index of the page table, and then page number will give you the index on the page table entry. Here you will find a frame number, which is frame number is actually the address of the physical memory, and there in you will reach here, you will find this particular address till you reach here, and once you club it with the offset, you will reach to the byte which is required by your process. So which process is reading that. So this is the whole address translation scheme which happens inside the virtual memory. I just want you to have a thought on this. Basically, you have any questions on this, Jitu? Because this is very important concept. Maybe it will be required most of the time. You will be dealing with the systems. Okay, so your question is how OS decides the size of the VM space. OS basically depends on the architecture. So you work on the different operating systems. Um, you will come to know how we actually it actually depends on the platform. So let's say the AIX system might be using 52 bit of 52 bit of your virtual memory addresses. Your Linux kernel might be using 48 bit of virtual memory address. So that actually architecture and platform architecture dependent. Second thing is deciding having so much of virtual memory will never solve a problem. Okay, page address translation, you don't have any. Okay. Okay, so VM size is not the solution of all your problems to map the addresses. If you keep so much of virtual memory, let's say you want to keep let's say 70 bit of virtual memory, and what, so I mean, if you keep that much addressing scheme, that means you are going to have more metadata of the processes, whether that metadata handling and that address translation is causing so much overhead on the system, which actually uh, we actually defies our purpose of having a multi-process environment to achieve the performance. So you need to find out a middle way where basically the system will we could be able to achieve the multi-processing on the limited RAM, and we could also get the fairly better performance. So once you see that the virtual memory, once you start increasing the processes in the system, there will be more page tables will lead to the more page table entries, and once that kind of page table entries are there, it is again like I mean, you're trying to read a address, so basically a process is executing on its own logical address space, but finding it on the physical address is again a whole task to be done by virtual memory manager, right? So in that case, you basically what you do is uh, you need to limit somewhere where you can maintain the data structures. So what is there? Okay, I was coming to the point where TLB comes into the picture, because you have lot of addressing here, right? Lot of page tables are here, lot of addressing are here, a lot of page table entries and lot of page table itself. So this is what um, the whole the whole what here is required is how you will find out the pages which is hit by multiple processes on the uh, very regular basis. So there would be some pages which is related to something like, okay, the segments, the pages which contains the text of some for loop, okay, maybe some functions. So that would be on some pages, and maybe that is required to be calling again and again, and mapping and getting the physical address again and again. So in those cases, what we will fill it up, we will have a TLB here, which is translation look aside buffer, which is used for maintaining those entries which are mostly used by our system. And TLB the first virtual address space, the hit is going to happen on the TLB. If it finds in TLB, it will find the actual address on the physical memory immediately. If it doesn't, then it will process the same thing to reach to the physical address. So that phenomenally increase the performance, because you don't need to go to uh, You don't need to actually go to the whole process again and again to reach one address. So we will look at it here. So each of your virtual memory reference basically, okay, so this is quite important. So you have virtual memory address with you, right? What you gonna do with that? Either you want to reach to a page table of that process, for which this virtual address belong to, and another thing would be like you want to fetch the data which is written on that page on the physical memory. So once you have that kind of calculation happening in the back end, it will cause a lot of performance setback for a system to execute a process. So what you introduce is a cache which will give you the most used places into the system, and it will, once a TLB hit happens, it actually so I think Jitu is dropped down. I'll wait for him to join. So okay, I was telling you about TLB basically. Uh, so basically TLB will be like cache hit and cache miss concept, the same concept. So what you do, the most used pages mapping will be kept into the TLB, and every time you have a virtual address with you and you want to reach to the data, you first do a TLB hit. If TLB hit happens, you will reach to the physical address immediately. If it misses, then you go through the whole process of address translation and reach to the data. So basically it's a hardware. TLB is a hardware which is actually provided by most of the processor features. So you have very fast cache on your board, which is supporting it. So basically it's a bit of software and a bit of hardware, which is helping you to achieve the performance of the system. And once you have TLB in the place, you can significantly see the performance up of the system, because this is how the system behave. You have some of the pages in the nature which need to be called again and again. Just assume as a text segment uh, of the process management or virtual memory. So these pages will be like uh, you know um, these pages will be like mapped called most of the time in the system. So having them into the address mapping and into the TLB hit will give a huge performance boost for the processes, and rest of the mapping of the pages can be done through the address translation, um, the whole process of that. So it is telling you the same thing. If the page table entry is not found in TLB, here I told you that TLB hit, the frame number is retrieved and the real address is formed, right? So you have a very fast cache TLB. Once you have a page table entry there present there in that TLB, you will immediately get the frame number, and you will attach it with the offset and find the location in the RAM, in the main memory. And if you have a TLB miss, it will follow the same procedure of the address translation what we have seen here, right? So once TLB hit happens, miss happens, it will go find out the page table, then it will find out the index, and then it finds the frame number. So this is quite a bit of things to remember, that we divide each process address space and the whole virtual address space into the pages, and we divide whole physical memory with the frame numbers. Okay, so it's the same size. Page size is 4K, and the frame size on the physical memory is 4K. Now you can have multiple page size also, but we keep the multiple of 4K if the frame numbers are divided into the 4K, or your whole physical memory is divided into the 4K frame number size. So you always keep the page sizes of the multiple of the 4K. That keeps you, that helps you to map it cleanly on your page table entries. So it contains, TLB contains the page table entries that has been most recently used. Alright, so the given a virtual address, processor examines the TLB. Okay, for TLB hit, it's try to form an address. If it doesn't find the TLB, it will process the same. So TLB and any page table entry. So what how you will find that particular page is present in main memory or not? So basically it is like you have a bit set which says you that this particular page is present in the physical memory or not. And if it doesn't if it doesn't present in the physical memory, basically into your RAM, then it will the virtual memory will trigger a page fault exception, which actually swap in the page into the physical memory and creates a mapping page table entry into the page table. So possibly this would be an exercise how the page fault exception works in the virtual memory. You can have it as an exercise. Write it down and send it to Chaitanya and me. Write it down the okay, I'll do that. That would be better. So because so you have So once you browse the source code of swap in, swap out, it will basically have lot of information like how it will uh, how it will get the page table index, then how it gets the page table entry number, and then how it reaches to the frame number. So some of the information dynamic in nature, something like once system is bring up, it must know how much physical memory it has, what is the physical memory layout it is putting in. Some part will go into the DMA, some part will go into the um, go reserved for the kernel, some part will go into the user space process and the buffer cache. So once it has laid out the architecture of your physical memory, it will have the information to keep. So these memory size and all is dynamic in nature. It will be identified at the runtime and given input from the BIOS basically. So so the same thing, uh, whatever I have shown you, the last diagram. I was showing you the last diagram how it will reach to the physical memory, uh, that physical memory from a virtual address. So the only thing here changes is a TLB, the translation looker recite buffer. So it's a parallel access memory basically. So you have if you have pages which are very frequent in use, will be kept, their mapping are kept into the TLB, and once the TLB hit happens, you will get the frame number immediately, and you can attach it, you can concatenate with the offset, and you will reach to the byte on the main memory. And if TLB miss happens, it actually process the page number and process it to the page table PTR to reach to the page table, and then the index on the page number will be given by page number in the virtual address. So it will do that. Once it reaches to the page table entry, it will find the frame number, and then that frame number is concatenated with the offset, and it will reach to the memory. And once the virtual address is found that this the page table the page is not present into the main memory, it identifies it here itself in the virtual address, a bit which shows that this page is swapped out or swapped in. So the memory, it will trigger a page fault and finds the relevant block in the disk, and process the IO to basically copy it to the main memory. And then once that main memory slot is reserved, it will create a page table entry for that. So next time you will have the page which has called which has triggered a page fault is now into the main memory, and next time you come and read for the same page again, you might find that page into the TLB itself. So so the algo, it depends on the algo which TLB uses most recently used, which is like recently dependent on the timeline, the recent pages, and the most recently is the number of times. So it is dependent on the two factors. the frequency of the accessing that page, and the second is the recent factor. So if it is a recent and the frequency is high, it will be kept into the TLB. So okay, so this is important concept of the fragmentation. Once so this fragmentation concept comes with so you have, let's say you have a chunk of memory. You have, I will move to the diagram. Okay, so let's say this main memory has I will divide this main memory to the larger chunks. Let's say I'll create a frame size of, let's say, 16 MB. Okay, but 16 MB will be the minimum the minimum unit which will be addressed by your page table entry. So even though you have very small data, you will always have the mapping of whole. This 16 MB will be used. So you have internal fragmentation in that, right? And external fragmentation would become like, if you have page number 16 here, and okay, I'm taking this example right now, but let's say your next page starts from here, so it will lead you to the external fragmentation. Let's say this much data one page cannot, if I have starting of the page from here, this external place is unused, which is causing a external fragmentation. So the concept is, if you reduce the size too much of the frame size, you can solve the problem of external fragmentation, but you will again introduce some internal fragmentation. But if you increase the size, you may fight with the internal, you may overcome the internal fragmentation, but and with the lesser page table entries, faster access, but you may lead to the external fragmentation problem. So this is pro and cons of the both approaches. So what most of the operating system does is they use larger size of page in case of you have larger chunk of data. So you will not spend much time on the page table entries, right? Because you will have less page table entries for the larger address space. And once you have a data which is in nature or very small, you will keep the smallest piece of the let's say 4K. So it's a smaller one, we manage it here. So you will have a bit of more page table entries. So pros and cons is there. Architecture and designs are meant to solve the problems, and both of the approaches will have some pros in some of the situations, and cons in some other situations. Okay, so you have any questions on this, Jitu? So let's go through the facts here. Smaller page size means less amount of internal fragmentation. Internal fragmentation obviously less if you have a smaller page size. Let's say 4K. Let's say if I reduce it 1K of page will have a lesser internal fragmentation, and uh, but smaller pages will actually increase the page table entries, right? Because you will have more pages for addressing the same number of memory addressing, and now increasing of the page table entries will cost you something to find the frame number to particular page number. right? So so this is what here it is explained. If you have a smaller page size, you have less amount of internal fragmentation. A smaller page size means more pages required per process, right? Because 32 GB you will have to um, have 4 M of 4 M of page table entries. If it is your page size is 2 to the power 10, which is 1K, right? If you have 4K of page, you will have 1024 multiplied by 1024, which is 1 MB of the 1 MB of the 1 M number of 1024 multiplied by 1024 numbers of the page table entries. So so each entry, if each entry costs you like 4 byte, then it would be 4 MB of the pages, right? Just going back to the picture. So here take an example. Here you have frame size of 4K, okay? You have 32 bit of process, which is 4 GB. 4 GB divided by 4K will lead you 1M. 1M is actually uh, number of the entries in the page table, right? And if you have 4 byte of the page table, one entry, it will be 4 MB of the page table, right? So did you get that concept? Because it is more okay, cool. So you have we'll look at the facts, because it is more likely to, more pages per process means larger page tables, right? Because you will have more entries in the page tables, because you are having this lesser size. This lesser size will leads you to have more entries here. That means a larger page table. Larger page tables will hit your will hamper your process drastically, right? Right. So okay, this space size theory I have already given in the form of, having larger dividing the frame size into the um, uh, dividing the frame size into the physical memory. So basically it all depends on your, the usage most of the time. Some of the modern operating system are dynamically changing the internal page sizing depending on the data. So they are data smarter. Some storage companies are using that that um, that's a configuration options. So let's say if YouTube is dealing with larger chunk of data, and let's say it is transferring you to 80 MB 90 MB of data, and if it is using larger page size in the back end in its distributed storage environment, it will have to uh, you know uh, it will have to maintain lesser metadata in terms, and larger page size will help them to retrieve the data faster. So the addressing will be reduced, and its whole effort will be reduced. But the only problem is you will not be able to do much of indexing inside that data. Let's say I have 40, I started using um, 32 MB of the page size. Now the user is looking at the YouTube video at the location, let's say 10th minute. So 10th minute it will read the whole 32 M of the first um, 32 M of the first page of that blocks, and the 32 M of the second. And if I increase it a bit more, let's say after 32 M it falls under, it will read the whole page again. So there are pros and cons, but basically we find we find a middle way where we will less consume ourselves into the metadata processing, more consume into the data processing. So data availability. So this is how we do it. Okay, so some of the page sizes you can see it here. MIPS architecture supports 4 kilobytes to 16 megabytes pages, right? Ultra Spark is having 8 kilobytes to 4 megabytes of pages. So Itanium is so this you have to understand that basically your page sizes is not just the software. It is basically a hardware support is also required. So once your processor is enabled to support large page support, then only you will have that kind of addressing scheme in backend. So Itanium is the latest processor. It is widely used by most of the basically most of the servers. It supports 256 megabyte maximum page size. It's quite big and useful in most of the large data accessing cases. So basically what it does, your kernel smartly manages the addressing scheme, and it uses dynamically, if the larger data chunk is there, which file system and what to use the larger page addressing. So this is how it is managed. You have any doubts, Jitu? All right. Okay, Jitu, give me we'll take 5 minutes 5 minutes of break. Okay, it's 4:28. We'll take 10 minutes of break and we'll be back and continue the rest of the rest of this slides. Okay, so you have a time of 10 minutes. You can refresh yourself. We'll be back. Okay. All right. Yeah, so this is not true in our case. So this is, I think, Windows address space. Linux address space I have already shown in the process management class, and that is true for that. This picture is not true for ourselves. So I have already shown the Linux memory manager. So your process address space is basically it is it has all the segments defined from which address range to which address, and where is the shared library object, where is text segment, where is data segment, and the heap segment growing, stack segment and heap segment is growing in the opposite direction. So that I have already shown to you guys. This picture is not relevant. I am sending you this slide also. Maybe this picture you can discard, but you can find it on any of the site. You can look at the 32-bit memory architecture of processes and 64-bit memory architecture. So most of the thing we have covered in memory already. What I really want you to exercise is It's these two things, that you have to browse the source code for the swap in swap out, and the second thing is you need to come up with your things, whatever your knowledge base says, that what happens when you run a binary in the system. Try to explore, try to find out, and try to write as much as possible, maybe a single line, but events should be sequential in manner. It should not be it is doing that, it is doing that. It should be sequential in manner. Okay, so I have done for the day today. I think uh, I think you can um, I'll send you this talk to you, and what we can do is, next class we will cover locking and interrupts, which is going to be our last 12th class and the last class for the certification. And after that session you will need to go through one of the project, which after that evaluation, Anil will be planning for certification. So this is what we are left with. I'm going to send this slide to you. Please ignore this particular slide because this is not relevant to um, Linux. This is wrong memory address scheme. So you can find the address scheme in the linux.org kernel org. There you can find the memory layout for 64-bit and 32-bit processors. Okay, so I'm done for the day. You have any questions, Jitu? Cool. So I mean, pour in your questions whenever you face any doubts, anything. We will focus on what, I mean, your questions, and we'll try to answer. Okay, all the best, and see you next week. Okay.